again. Okay, so hey everyone, I am going to do a short recitation, optional for you, because some of you asked me to talk about how sensitivity analysis works in duality. So in this short video, I will, hopefully short, I will tell you about how sensitivity analysis works in duality and how that gives us useful information when the optimization problem in consideration changes somehow. So before that, I will do a very quick recap of what we did in the recitation. So keep in mind that we were trying to solve some sort of primal problem. And for this primal problem, we were trying to minimize some objective value f naught x subject to a number of inequality constraints, right? M of them. And for simplicity, we will assume that the optimal value is finite and optimal solution x star exists. Okay, so our first step was that we went back to Lagrange's time when we could not solve optimization problems because we did not have solvers, but we knew calculus. So Lagrange's idea was that he took the optimization problem, and created a penalized version of it, which was the Lagrangian, right? So the Lagrangian, what is it? You take the objective, you take the inequality constraints, multiply each inequality constraints underlying function with some positive penalty parameter, lambda I, which is also known as the dual multiplier, and add all these things together. And when you do that, then this Lagrangian kind of becomes a penalized version of the original problem. Why? We showed that if we have the constraint as particular constraint fix, if it is violated, then because lambda I is positive, lambda I fix will introduce a penalty in the Lagrangian. So it will end up increasing the cost function value of the Lagrangian. On the other hand, if our constraint fix is obeyed, then because lambda I fix is positive, it will introduce some sort of substitute, right? Reducing the cost, because in that case, this will be something that's less than equal to 0. Okay, so this is the penalty interpretation of the Lagrangian. So of course, Lagrangian is like a proxy of the original problem. So what we are going to do, we will minimize that proxy. So that was Lagrange's idea for some sort of, for a given penalty parameter set lambda I, which is also known as the dual multiplier. Okay, so if you do that, then we found that this dual function, which you minimize essentially the output when you minimize the Lagrangian for a given lambda, which is greater than equal to 0. And we showed that this Lagrangian is sort of an easy problem because the Lagrangian dual function is a concave function. Okay, so this led us to weak duality. And what does weak duality say? Weak duality says that if we take, so it has two steps. The weak duality has two steps. First, if we have a feasible x for the original primal problem, and if we pick any positive dual multiplier. So when I say positive, I mean greater than equal to 0. And if I say strictly positive, so that means greater than equal to 0. So, and if I pick any positive lambda, then we can show that the dual function will always be smaller. Like in terms of its value, it will always be smaller than the objective value of the primal for that specific feasible point x. So now because x star, which is the optimal solution of p star, because this is also a feasible point for the primal, so from that we could say that g lambda is always less than equal to p star. And this kind of leads us to weak duality. How? Because this is true for any lambda greater than 0, we also have the following true for any, not for any because we are maximizing. So the maximum over all lambda when we are maximizing the dual function will be less than equal to p star. So if we call this thing d star, which you are seeing here, so this d star would always be a lower bound for the optimal value of the primal problem. So this is the weak duality which holds irrespective of the convexity of the original primal problem. Also, another very nice thing about this dual problem is that the dual problem is always convex. So this specific problem is always a convex optimization problem because we are maximizing a concave function. Okay, so this was basically weak duality. And what is strong duality? Strong duality is when let me go back to strong duality. Strong duality is when both the primal and the dual problem have the same optimal value. We say that strong duality holds. And at strong duality, d star, the optimal value of the dual problem is equal to p star, which is optimal value of the primal problem. So it doesn't hold in general. Under regularity conditions, it usually holds for convex problems. And for convex problems, it may not hold, but those are kind of pathological conditions. And in the interest of simplicity, we will assume that like we are not discussing them like in this recitation. Okay, so roughly speaking, this is what we covered in our previous recitation. Okay, so now today we are going to talk about what happens when we perturb the primal optimal problem by some amount. So remember, this is our primal problem. So if you look at this one, so this is the primal problem that we studied in the previous recitation. Now, this inequality constraint. So do you have any questions so far?
Nope, sounds good.
Sounds good. Okay. So okay. So this inequality constraint, often in practice, they somehow correspond to some sort of budget. That you have two variable and like their sum has to be less than equal to some budget value. So this type of inequality constraints in practice, like it could be engineering, finance, and whatnot, they kind of correspond to some sort of budget that is imposed on us due to structural reasons or financial reasons or whatnot. So this could be something like this, that okay, the sum of these two variables has to be less than equal to 10. So what does that mean? So that in our format, we always write it x1 plus x2 minus 10 less than equal to 0, right? Now, for some reason, it could happen that new data comes in or the finance industry, something happens there. So whatever this constraint was, it changes by some amount. Now, this is what is reflected in this perturbed problem. So this problem, which we are denoting by P star U, we are trying to minimize the same objective f naught x subject to fi x, but now it's not less than equal to 0. It has been perturbed by some amount ui. And we call the optimal solution to this perturbed problem, which we denote by PRT, by x star u, like the optimal solution corresponding to the perturbation vector u. Now, what does that mean? So look, one thing. So let's take this specific constraint. So suppose this x1 plus x2 minus 10 for somehow, this is our first constraint. And let's say this u1 in this case is 2, right? It's a positive number. So what does it mean? So that means that, okay, like x1 plus x2 less than equal to 12 now. So in other words, this budget has been relaxed. So where I was limited to 10, now it has been, I am given some more independence in terms of like what value I could pick for x1 plus x2. So this is called relaxation of the inequality constraint, right? Okay. Another possibility is that rather than positive, it could be negative too. So let's take one example for that, for the same constraint. So let's say x1 plus x2 minus 10, and u1, the budget perturbation is, let's say, minus 1 now. So if this is the case, so then x1 plus x2 is less than equal to 9. So in this case, what has happened? Like my budget is tightened in a way. So uh, so if my UI is positive, so then it means relaxation. So in a way, I am given more room to optimize. And if UI is negative, so I am given less room to optimize. And what is our goal in this video is, our goal is trying to understand if we just solve this problem, is it possible for us to derive some non-trivial information about the partner problem? So this is our goal, because it could happen in practice that, okay, like this primal problem could be a very large optimization problem. Maybe it takes hours to solve. And you solve that problem, and for some reason your budget constraints change. So without solving the new problem NU, can you infer some valuable information just by looking at the dual multipliers of the dual problem? So this is what our goal is. Okay, so any questions so far, like about the motivation?
No, I think that makes sense.
Okay. Yeah, don't be shy, ask question, okay?
Okay.
Okay. So the first thing that we will look at, and which is going to lead us to the sensitivity interpretation, we will start with a global inequality. So what does this global inequality say? And we will actually look into its proof, which is very short. So suppose you solve the original optimization problem that does not have any perturbation, right? So by original optimization problem, I mean this one. So we have solved this. And when we solve this, we also solve the dual, right? And let's say the dual multiplier corresponding to all these inequality constraints is lambda star. Okay, so this is what I mean when I say here that lambda star is the optimal dual variable for the original problem. Okay, if this is the case, then the optimal value of the perturb problem can be lower bounded if I have the optimal value of the original unperturbed problem minus sum of all the dual variables of the unperturbed problem, mind you. So these are the different component number 1 of the optimal dual variable, component number 2, and so on, but corresponding to the unperturbed problem, the original problem. And this U1, U2, and UM, they correspond to how much the inequality constraints were perturbed, right? So these UIs are coming from here. Okay, and we will see that this actually does give us valuable information. But before I go into that, let us take a look at the proof of this fact, which we will see is very simple and kind of educational too. Okay, so now suppose we have some feasible x tilde for the perturbed problem, not the original problem, the perturbed problem. And we want to connect this feasible x tilde with our unperturbed problem. So in the context of simplicity, we will assume that the problem is convex, the primal solution exists, the optimal primal optimal value is finite, and so on. And because it's a convex problem, so we will also be assuming that those pathological conditions under which strong duality does not hold, we will not assume that, we will assume strong duality holds. So under those conditions, we can say that P star 0, right, which is the unperturbed problem's optimal value, is equal to the dual optimal value, which we denote by G lambda star. So by definition, the dual function's optimal value is essentially minimization of the Lagrangian, but for lambda, we put lambda star, right? So this is the Lagrangian being minimized, but at lambda I star. Okay, so now from going from this line to this line, what is the underlying logic? The underlying logic is that this is the minimization of this function over all x. So no matter what x I pick, if I pick any other x, like I can only get something that is greater than or equal to this value. So because x tilde is any such point, I could just set. I could just take this objective function, and there I could get set x tilde, and what I would get will be greater than or equal to like what I am minimizing here. Okay, so from this line to this line, is the logic clear?
I think so. I might have a question though. So,
Okay,
but you've picked x tilde from the feasible set for the perturb problem,
right.
but it's not necessarily feasible for the original primal problem.
Exactly. Yeah. So keep in mind that for sure. Now keep in mind that this problem is an unconstrained optimization problem, right? So feasibility does not have anything to do with this. So basically what it says is,
Right.
so this is by definition, right? So if I minimize any function with respect to x, no matter what point, by definition, this has to be smaller than equal to fy for any y, right? So this is the definition of minimum.
Yeah, okay.
So all I am doing, so if I know this, so I know that this is minimum of x over, like minimum of this function over all x, right? So I could take like any point. So let's say I pick an arbitrary point y. So by definition, this has to be, don't look at this line, just look at what I am writing. So lambda I star fi y. This is true for any y I pick, right? By definition.
Right, okay, yeah,
Right.
that makes sense.
Right? So then this is true for all y. So I could just pick for my y, I will just pick x tilde, which is another point, right? So that basically, this is y. So all I am doing, because this is true for all y, I am just setting y equal to x tilde, which is leading to this line.
Okay. Makes sense, yeah.
And does it make sense? Like, think about it, because
yeah, that makes sense.
okay. So we are at this point, we are at this line. Okay. So now carefully remember that x tilde is a feasible solution for the Perturbation problem. And what is the Perturbation problem? The Perturbation problem looks like this, right? So we are minimizing f naught x, fi x less than equal to uy. So because x tilde is a feasible point, so fi x tilde would be less than equal to uy for all I 1 to m, right? So based on this, we can go back. So here I am using the fact that fi x tilde would be less than equal to uy. By definition, the dual multiplier is positive. So as a result, from this line to this line, this will not change the inequality. So when I go from here to here, I am basically getting f naught x evaluated at x tilde plus sum of lambda I star uy. Okay, and so basically, we have shown that p star 0, which is the optimal value of the original problem, is less than equal to f naught x tilde plus lambda I star uy. And this is true for any feasible x tilde of the Perturbation problem. Okay, so now, because x star u, which is the optimal solution of the Perturbation problem, it has to be feasible by definition. So in this inequality, I could just consider x star u, and this would still be true, the previous statement. So this is what I am doing. I am setting x tilde in place of x tilde. I am setting x star u. And when I do that, what I am getting p star 0 is less than equal to f naught x star u, which is actually p star u plus the sum of the lambda I star times uy. So from that, I will just changing sides of this p star u. I am getting p star u is greater than equal to p star 0. So this should be, let me correct this. P star 0 minus lambda I star ey. So this is what we actually wanted to prove. So any question about the proof logic, because this is going to be important. for the homework or midterm.
I think that makes sense. Yeah.
Okay. So what is the interpretation of this? So the interpretation is that, first of all, this is giving us a lower bound, right? It's giving us a lower bound on the optimal value of the perturb problem. It is not giving an upper bound, but still it gives us interesting information. Suppose we solve the primal without any perturbation. We find the dual multiplier, and for a specific constraint, we find that lambda I star is big, like it's a large positive number, like it's like 10,000 or something like that. And then the inequality constraint corresponding to that lambda I gets perturbed in a way that the budget is tightened. So you have less room to optimize now. So when you have less room to optimize or less room to minimize a cost function, then what is going to happen? So you intuitively understand that you don't have as much area to optimize. So your optimal value, right, optimal or the minimum value is going to go up. So the thing is that, of course, that makes sense. But if the dual multiplier is very large, it will go up by a significant amount, even if the amount by which you tightened your budget is small, which is EY. Even then, this one tells you that your P star U actually will be large. So essentially saying that the dual multiplier, if you tighten, if the dual multiplier is very large, and if you tighten your budget even a little bit, your optimal value actually will go up, will be. So you cannot do anything about that, which is kind of non-trivial, even though the math was kind of simple to understand. Okay, so now the other case, so it's why I don't know why I wrote 3, it should be 2. Other case is lambda I star is very small. You solve the optimal, you solve the unperturbed problem, primal and dual, and you found that lambda I star is very small, and UI is positive. So positive means what? Like you are relaxing the budget, right? So you have more room to optimize now. So your P star U is going to decrease. Now, when lambda I star is small, this one is this inequality is telling you that P star U actually will not decrease too much, because because lambda I star is value is kind of small. So even though this inequality was just giving us a lower bound on the optimal value of the perturbed problem, it still gives us to me they are non-trivial, because to understand that we actually don't need to solve the new problem. And I don't know, it could be something, let's say if you're working in finance, right, and you're trying to minimize cost or something like this, especially this thing, the first one could save you a lot of money, right? So that was the interpretation of this, and then we will go into local sensitivity analysis. So this specific equation that we covered, so this called global sensitivity. So any question about this one?
You're saying P star U will be larger, but like just the lower
yes.
bound has gone up, right? Like it doesn't necessarily mean that the actual value is.
So that you are asking the question about the first one, right?
About the first one, yeah.
Yeah. So this one actually is telling you definitively it will go up by significant margin. So let's take a look one example. Let's say we have found, let's call the first constraint, suppose lambda 1 star, and you found that it's like 10 to the power, let's make it very large, let's say it's like 10 to the power 10. Now, and you solved your P star 0, like you want to save money, and let's say my P star 0, like you did it successfully, so your P star 0, let's say 100, like This is your optimal cost.
Okay,
right?
sure. Yeah.
Now, what is happening? And let's say your U1 is 10. Okay, so whatever the budget was, I don't know, let's say is sum of some resources, and you have, let's say, I don't know, n resources, and they're less than equal to 100. Suppose I'm making this example up, by the way.
Mhm.
So this is like 100 unperturbed problem. So what would be the perturbed problem? So that would be like, because U1 equal to 10, so this is unperturbed. Let me call it unp, and the perturbed version would be I from 1 to n xi less than equal to, so negative. So I will make it negative because in that case you see, so it everything kind of changed the same, except that this budget has gone down a very little bit, right? So it was 100 before, from 100 now it's 90. Now what does this theorem tell us? It tells us that, okay, like even though, and let's say every other constraint that were not perturbed, so then your new p star, under the condition that U1 is equal to -10, so you just perturbed, you tightened the budget of your first constraint by 10 units. So what is going to happen is actually is going to be larger than p star 0, which was 100, and minus your first dual multiplier lambda 1 star. So this, its value is 10 to the power 10, right? 10 to the power 10, and then you take this minus 10. So essentially what it's saying is like, this 100 does not even matter anymore.
Yeah, it's significantly going to go up. Yeah.
Yeah. So it's like almost a blowing up effect that is happening.
Okay.
So, and what does it actually mean? Like in practice often it actually means that you did not model reality that accurately. Like when so you change your resource by a very small amount, and this is having such a large effect on your new objective value. Like, think about it, if this was a small farm, it will actually go out of business, right? So
yeah, there was like some large unaccounted risk basically that you didn't model
associated
properly.
with that. Yeah, so it could happen. I hope that does not happen to real farms. Yeah, but it does it's giving you something very definitive. Okay, so if you don't have any questions, so now I will talk about local sensitivity analysis.
Sure.
Okay, so now let's talk about local sensitivity analysis. So here, one assumption. So the global one is very global in the sense that, like, it's not telling us anything about how much we changed, how much we perturb. This perturbation could be very small, and the perturbation could be very big. So the local sensitivity analysis tells us that if your perturbation is very small, then we have something neater. Okay, so we will make this assumption that p star u is differentiable around u equal to 0. So this is an assumption, keep in mind. And also, like, even if you don't have this assumption, you can build similar sensitivity analysis, but we don't have the machinery to study that yet. So we will stick to differentiability at that point. If this is the case, then the dual multiplier lambda has a very nice interpretation. So it says that lambda I star is equal to, so this is something we were going to prove, is equal to negative of the partial derivative of the p star, the optimal value around 0, subject to your perturbation. And if I use slight abuse of notation, with that abuse of notation in mind, this gives us something very neat. It tells us that the change in cost, right? Like, so 0 is the unperturbed case, and you perturb your constraints, let's say constraint number I, by a very little amount. If you do that, so then your change in cost is kind of controlled by, of course, this makes sense, how much you changed your uy, which is the perturbation, times the negative of the dual multiplier. Intuitively, as of now, like we will see the proof, but even without the proof, we see it kind of makes sense. So if your change in ui is negative, that means you tightened, because this is a positive thing, like this dual multiplier. So the entire thing will be positive. So your changes cost is positive, that is cost is going up. And then of course it's like, if this change in UI is positive, that means you are relaxing. Then because this is a positive, the dual multiplier is a positive thing, so your cost actually will go down. And even here, there is a very interesting thing, that we are assuming that around zero, right? So that is zero, no perturbation situation. You are perturbing the ith constraints a little bit. But again, it's telling you that if lambda star is very large, it can have immense effect. Okay, so let's try to look at the interpretation. So under regularity condition, why I am saying regularity condition? Because we are assuming, like differentiability around zero, strong duality holds and all this. So that's why I'm calling under regularity conditions. Optimal dual variables, they are exactly local sensitivities of the primal optimal value with respect to amount of perturbation, right? So this is linguistically how we would express the formula that we saw. So of course, this is something I already told you. Tightening the ith equality constraint is corresponding to ui less than equal to 0. So this is going to lead to an increase in cost. If I loosen the ith inequality constraint, this should be positive. Then the cost will go down. So this is the interpretation. So any question about that? And after that, we will take a look into how this thing is proven.
No, that makes sense.
Okay, so let me have some water. And then so to go to the proof, so we are just going to do a quick recall of what partial derivative is. Keep in mind, in this, we are actually taking partial derivative. So let's just refresh what the definition of partial derivative is. So we have a function phi that is, this input is from the Euclidean space Rn to R. And let's say we pick a point, n-dimensional point, A, with components A1, A2, and An. So it has like n number of components. And our notation EI denotes that it's a vector with n components, because we are talking about n-dimensional space, where every element is 0, except in the ith position, we will have a 1. So this is a very standard notation. So the partial derivative of the function phi around the point A, right, with respect to the variable xi, means that this is like a program. This is how we compute it. So what it means? It means that around the point A, so A has many components, right? So A is essentially A1, A2, AI, AN. So this is the point around which we are taking the partial derivative with respect to ith variable. So and what does A plus HEI mean? A plus HEI means that every element stays the same, except the ith element, we are adding H, right? And everything else is staying the same. So we are evaluating phi at that point, right? And we are also evaluating phi at A. And then we are subtracting like how much the value change. And then we are actually dividing it with how much we change the input component, which is h. So when you do that, we divide and then make h infinitesimally small. And the resultant number that we get, that is what we call the partial derivative. Any question about the definition?
Nope, makes sense.
Okay, so let me quickly pause the recording. So okay, so now that we have refreshed our memory of partial derivative, so let's start the proof. So in this case, what we are trying to do, we are trying to compute this quantity, right? Like del p star 0, because like we are perturbing around 0. So that's why this is, we are interested in the characteristic of the optimal value function when there is no perturbation. And we are interested in computing the partial derivative with respect to ui, which is amount by which we are perturbing the ith inequality constraint. So, okay. So what we are doing, we are picking the perturbation vector u equal to TEI, because this is just to plug in into the definition where all the elements are 0 except the ith element is t. And for now, first we are picking t is greater than 0, and then we will pick t is less than 0. Okay, and then we will arrive at the inequalities. But for the first case, we are starting t is greater than 0. Okay, so at this point, del p star 0 partial derivative with respect to del ui is equal to limit t goes to 0, and this is just the definition, right? Okay, so now recall that we just proved in the global inequality thing that this is always true, that if lambda star is our optimal dual variable for the original problem, then p star u is greater than equal to p star 0 minus lambda star transpose u. Because recall that this is, sorry, I should say like star should be here. So lambda star t u, lambda star ith component, uith component, and sum over all the constraint. Okay, so let me fix this quickly. Transpose u. Okay, good. So this is something that we proved already, and we know this to be true. And we are going to see how this equation part can be manipulated using this inequality. So in this, we are going to set u equal to TEI. That is, we are only changing the ith inequality. We are perturbing that by amount t. Everything, every other constraint, they are staying the same. If this is the case, also like in this case, remember t is greater than equal to 0. So if this is the case, so then I am just plugging that in, right? Nothing fancy going on. After that, what I am doing, because t is strictly greater than 0, I can say p star TEI minus p star 0 divided by t would be greater than equal to minus lambda I star. And because t is a positive number, dividing by it will not flip the sign of inequality. Okay, after that, I have this equation. What I am going to do, I am going to take limit on both sides. In this case, it does not involve t, so it will basically stay the same. When I take the limit on this side, this is by definition, right? This is by definition del partial derivative of p star 0 around ui. I'm just using this specific equality, right? And this is essentially just definition. So if I put it here, so I am getting del p star 0 with respect to del ui is greater than equal to minus lambda I star. Okay, so we have proven one side. So now we are going to consider the other case where t is less than equal to 0. When this is the case, we kind of start similarly. Like we take the global inequality and take p. So essentially, I am putting u equal to TEI again. Now, because t is negative now, when I divide by t, this inequality that you are seeing, it flips, right? Because division by a negative number flips the inequality. After that, I am taking limit on both sides again, and using the definition of limit, I again get the partial derivative. Now is in this case is less than equal to lambda I star. Now, essentially both of them, if I look at 1 and 2, the first one is saying that the limit is greater than equal to minus lambda I star. And in this case, I am seeing that the limit is less than equal to minus lambda I star. So the only possibility is that the limit it has to be equal. And this leads us to the local sensitivity proof. Okay, so any question about this? And let me have some more water.
Looks good.
Can you reproduce it if I ask you?
Maybe.
Okay. So let's try to understand the implication of this local sensitivity analysis. Okay. So so there are 3 implications that we can get. The first implication is we solve the unperturbed primal problem. Okay. And we find that the inequality is strictly less than 0, like the ith inequality, which we are eventually going to perturb. So then what it implies from complementary slackness, remember one of the condition, the fourth condition of the KKT condition was that lambda I star fi x star is equal to 0. So if I have this strictly less than 0, so then lambda I star has to be equal to 0, right? So what does it mean? So that means that as long as change in EY is small enough, then even if I like it is not going to have any effect in your cost. So because no matter how much you change, like when I say how much you change, is like keeping in mind that like all this mathematics is actually true, keeping as long as the change is small enough. So within that regime, does not matter how much you change it. Okay, so I don't. It sounds paradoxical, but in that regime, even if you change your constraint by some amount, it's not going to have any effect in your cost. So if you are running a business, it's kind of telling you that, okay, like you have some independence, like in this budget constraint, right? Like even if you increase or decrease a little bit, it's not an essential constraint. It's not one of those constraints that, like things blow up and whatnot. Okay, so this is the implication number 1. So now let's take a look at the other 2 implications. Let's say, so I'm going to pause the recording again. So I need to drink some water because I feel. Okay, so I am back. So we will look at the other 2 implications. So what does the other 2 implications say? So in this, we have 2 situations. One is that lambda I star is very small, or lambda I star is very large. Why I am saying fi x star is equal to 0? Can you tell me why this is like automatically true if I say lambda I star is very small or very large?
Because one of them has to be 0, right? So
yeah.
lambda.
Yeah. So So because this is complementary slackness is great. Yeah. Okay. So what is going to happen when lambda I star is very small? So then it says that if lambda I star is very small, then I can change my UI. I can have a small perturbation without affecting change in cost, right? So in this case, remember, like I actually would have no effect. Here I can change it a little bit, and the effect will be like small. This is the case like where this is like one of those, like, I don't know, black swan cases that you have to be very careful about. So this says that even if you change in, you have a very small change in UI, because lambda star is very large, and it can be very large, right? Because like even with this realm of very small perturbation, if lambda star is very large, it's actually something to be very careful about. Like this is a constraint that you don't want to mess with. If you do, like, I think it means there is some sort of very messed up sort of non-linearity going on, like in the underlying problem structure, that like you change this dual multiplier is somehow encoding that this specific constraint is convex, but still it probably has a deep non-linearity in it that can lead to, I don't know, like a mess. So because you are actually in the realm of local sensitivity, and still it is kind of allowing you a tremendous change in cost. So you always have to be very careful when you see, like you solve a primal problem and you find one dual multiplier is like insanely large. This is like you have to be careful messing with that specific constraint or perturbing it, because it is going to change things significantly. Okay, so this is essentially the sensitivity analysis. So do you have any question like on the basic mechanism, how it works and so on? Like did the proof make sense?
Yeah, it all makes sense.
Okay. Okay, so the main part of this is over. One thing that I am just going to cover, and it's very very trivial actually, but I think it needs to be mentioned, that like in the lecture so far, you have seen that I told you that we only like in our analysis and everything, we only considered inequality constraint, right? And previously I told you that if I have, so in this case, you see I have inequality, but also equality constraint, right? And what was the recipe that I told you? I told you that the recipe is you write down this equality constraint as two inequality constraint of less than equal to form, and then you proceed. Now, if it turns out that, you know, like you have to do it in exam pressure and whatnot, this works. It will always work, like writing it in inequality form, but it is also increasing the load on your working memory, right? You have more constraints to deal with and things like that. So now the question is, can we keep the problem as it is and then construct dual and Lagrangian? The answer is yes, of course we can. And this also can be built from first principle. So first, let us try to write down our Lagrangian, because after we have written down the Lagrangian, then every other step is the same. So we will start with this form, right, that we know of so far. And for this constraint, the dual multiplier is lambda I. For hix less than equal to 0, the dual multiplier is alpha I greater than 0. And for minus hix less than equal to 0, the dual multiplier is beta I, right? And all of them, they are non-negative. Okay. Now, how we would write down the Lagrangian? So you have our variable x and three dual multipliers, lambda, alpha, and beta. All of them are positive. So we proceed like before. So we write down the optimal, the objective value, not optimal, sum of all the inequality constraint number one, those functions times lambda I, alpha I times hix, beta I times minus hix, right? Now there are p of these constraints, right? So we can actually write down these two summands into one sum. So if you go from this line to this line, the first two terms are the same. and these ones we are collecting under the same sum. And if we do, we see that because hix is we can take as common, and we get alpha I minus beta I. Now here we are going to use something that is kind of trivial, but needs to be said, is that what is alpha I minus beta I? So we said alpha is greater than 0 and beta I is greater than equal to 0, right? So alpha I minus beta I, if we don't have any restriction, right? If we pick any alpha I positive, any beta I positive, then alpha I beta I actually will be a sign-free number. It will be a free variable. Why? So if you look carefully, no matter what number you pick, positive or negative, it can always be written as subtraction of two positive numbers. So suppose 5. I can always write it like 11 minus 6, right? Like subtraction of two positive numbers. Let's say minus 2. Again, I can write it subtraction of two positive numbers, right? So do you see any number can be written as subtraction of two positive numbers? So that's why if alpha I and beta I are free, not free, like positive variables, then alpha I minus beta I over all the values of alpha I beta I that I could pick actually will be a free variable. Do you have any question about this? Because this is the key observation.
Right. No, it makes sense, I think.
Okay. So roughly speaking, what we are going to do, rather than this alpha I minus beta I, we will just call it a new variable, because this is, look, if you look carefully, alpha I and beta I, they going forward, if we took the dual and everything, they would actually never appear alone. So they will always appear like alpha I minus beta I together. So I can just define them as a new variable, because if I wanted to take the dual function now, what the dual function would be. So I'm showing it on the left side. So it will be lambda alpha beta. And what the thing is, it is minimum over x, right? And this will be this thing. So I will be minimizing this thing. Like whatever this minimum is actually will be this term. And if you look carefully, alpha and beta, they are not appearing separately. They are appearing always as the subtraction. So I can just replace them with a new variable, new y, which will be free. It would not have any sign of its own. So this I could define as the new Lagrangian. Okay, so that gives us the way of dealing with equality constraint without rewriting them as two inequality constraints and so on. And I just wanted to quickly discuss the recipe. So the primal problem, right? In this case, we are not going to rewrite them. We will just define the inequality constraints. Again, we assign a positive dual multiplier, lambda I, and for the equality constraint, we assign a free multiplier. This is also a dual multiplier, but it does not have any positive or negative sign. So what the Lagrangian would be, after that is everything the same. So essentially the Lagrangian would be x nu lambda, lambda nu equal to the objective times the lambda I times fix sum, and then nu I times hix sum of them. Dual function again is like maximum over minimum. It should be minimum, sorry. Yeah. So minimum over x, lx lambda nu. And the dual problem will be, I will be maximizing over g lambda nu subject to lambda greater than 0, and nu does not have any sign restriction on it. Okay, so this is how we would take dual for problem with equality constraints. So this is the recipe. Okay, so with that, the recording ends, and hopefully it gave you some idea about how sensitivity analysis works. And yeah, and if you have any question about the recording or if anything else, please let me know. Thank you very much for watching it. Okay, so I will stop the recording now.